Well, students, right here again. Day, section 3.3, phase changes. Start with characteristic of phase changes and get a definition for phase change. Phase change, the reversible physical change that occurs when a substance changes from one state of matter to another. And 6 common phase changes. You need to know melting, freezing, vaporization, condensation, sublimation, deposition. And as we go through, we will explore each of these. Get a little diagram here illustrating the phase changes. Solid to liquid, melting and freezing. Between gas and liquid, we talk about condensation and vaporization. And between gas and solid directly, without going to the liquid phase in between, we talk about sublimation and deposition. Put down a little chart like this in your notes. Some of the arrows are red, indicating energy is being added. Some of the arrows are blue, energy is being taken away. What happens to a substance temperature and system's energy during a phase change? Another key question. Temperature, very key point, one that's not necessarily intuitive. The temperature of a substance does not change during a phase change. So as we have a little container of water, and we put that in a freezer, that little container starts to form little ice crystals, and it continues to freeze till it ends up being solid ice. As this process is occurring, as it's going from liquid to solid, the temperature is always 0 degrees Celsius. 0 degrees Celsius. 0 degrees Celsius. So it's in that process of changing from liquid to solid, or it could be melting from solid to liquid. 0 degrees. So if you see a mixture of ice and water that has reached equilibrium, it's at the freezing point. So a heating curve, if we take naphthalene and we start heating it up, naphthalene, its temperature's rising, and it gets up here and it just flattens out. And then it starts to rise. This is its melting point of 80 degrees Celsius. So until it completely melts, temperature stays at that 80, then it starts to go up again. If the naphthalene was cooled, the temperature will drop until it reaches 80 degrees Celsius, and then it stays at 80 degrees Celsius till it freezes. So the temperature at which a substance freezes, its freezing point, is identical to that at which it melts, its melting point. Same thing happens as it reaches boiling point. The liquid naphthalene was heated, its temperature is going to keep rising until it reaches 218, boiling point of naphthalene, and then once it completely boils, as it's boiling, temperature is going to remain at 218 degrees Celsius. Energy is either going to be absorbed or released during an energy change, depending on which way we're going, or during a phase change. So there's some ice sculptures, placed up in Alaska in Fairbanks. So Sunlight shines directly on it, it adds energy, can cause it to melt. Or if the temperature rises above zero, it's going to melt. But energy, added energy, can cause these things to melt. And we use a couple fancy terms during an endothermic change. It absorbs energy from its surroundings. Melting, endothermic change. And then as it's melting or freezing, it adds energy. And in this case, for 1 gram of ice, 334 joules of energy, and this is called the heat of fusion for water. Going to vary from substance to substance. Energy is released as ice forms on the strawberry plants from freezing temperatures slightly below 0 degrees Celsius. Actually, we'll spray water on plants to protect them if the temperature drops down to freezing. So as water freezes, it releases heat. The flow of heat slows the drop of temperature and helps protect the crops from damage. And then we got an exothermic change. System releases energy. Freezing, exothermic. The other key question, how does the arrangement of water molecules change during melting and freezing? Arrangement of molecules in water becomes less orderly as it melts and more orderly as it freezes. So in ice, attractions between water molecules keep them in fixed positions. And any energy gained increases the average kinetic energy, and the temperature can go up. And as temperature goes up, the molecules can start moving around more. They vibrate more quickly. At 0, some of the molecules gain enough energy to overcome the attractions and move from their fixed positions. When all the molecules have enough energy to move, melting is complete, and we are at the liquid phase. So when we think freezing, we generally think it's really, really cold, but different things freeze. Here's an example. Silicon freezes at 1,412 degrees Celsius, which is 2,574 degrees Fahrenheit. So things can freeze at things that are solid at room temperature, can freeze pretty high temperatures. So freezing is actually just a change from liquid to solid. It can occur at a variety of temperatures for different substances. When liquid water is placed in a freezer, energy flows from the water to the air in the freezer and the water cools. Average kinetic energy is going to decrease, they move slower. The freezing point, some molecules slow enough for the attraction between molecules to have an effect. And they start holding them into place. And when all the molecules have been drawn into that arrangement, the freezing is complete. We got vaporization and condensation. We go from liquid to gas, we're talking vaporization. Endothermic. 1 gram of water gains a little over 2,000 joules of energy when it vaporizes, and we call this the heat of vaporization. Again, varies from substance to substance. In the refrigerator, phase changes keep the food cold. Energy from inside the food compartment is used to change a liquid to gas in the evaporator, Energy is released when the compressed gas changes back to a liquid, and that energy is released to the outside. So we just got a pair of phase changes going on here. We got the evaporator causing energy to move in there. Then it's moved around here where it's compressed and energy moves back out. Evaporation changes when a liquid changes to a gas. Evaporation you'll see puddles of water disappearing. Got some key changes between evaporation and boiling. Evaporation takes place at the surface of a liquid, occurs at temperatures below the boiling point. So, here, water molecules at the surface of this bird bath can jump out into the atmosphere, and that's what's causing the evaporation, and it'll happen at temperatures below the boiling point. That pressure caused by vapor formed when a liquid evaporates is called vapor pressure. As the temperature increases, the vapor pressure increases. Water molecules have enough kinetic energy to overcome the attractions between the molecules, and they move into their gaseous phase. And key question, how are evaporation and boiling different? At 100 degrees, some of the molecules on the surface of the liquid and the water have enough energy to overcome the attraction between the molecules. Because water vapor is less dense, the bubbles quickly rise to the surface. When the vapor pressure becomes equal to atmospheric pressure, water boils. So water boils at the boiling point. And it takes place throughout a liquid. Read earlier that it evaporates at the surface of the liquid and evaporates at temperatures lower than the boiling point. Some other differences be evaporation tends to be a fairly slow process, where boiling tends to be a much faster process. And boiling point depends on the atmospheric pressure. At sea level, water boils at 100 degrees Celsius. You get to higher elevations, boiling point is lower than 100 degrees. If you Google like boiling point at the top of Mount Everest, you're going to find it's a lot lower than that, because the atmospheric pressure is much lower. So you can Google boiling point of water in various places, and you get some that are high, like top of Mount Everest. Denver, Colorado, other cities with high elevations, you'll find a lot of different boiling points for water. Condensation, when changes from a gas or a vapor to a liquid. Condensation, exothermic. Condensation, say dew or fog, due to condensation. Dry ice. Common name for solid form of carbon dioxide. Solid carbon dioxide does not form a liquid as its temperature changes. At room temperature, dry ice changes directly from a solid to a colorless gas. Sublimation is what we call this change. There's our definition. Sublimation, endothermic. As dry ice sublimes, the cold Carbon dioxide vapor causes water vapor in the air to condense and form clouds. So that's what gives the fog, like on a fog machine you might have seen at the dance. And there's a mosquito trap. Mosquitoes are attracted to carbon dioxide, so putting dry ice in this trap detracts the mosquitoes. When a gas or a vapor changes directly to a solid without first changing to liquid, phase change is called deposition. Reverse of sublimation. This causes frost, causes some snow. Snow can be some mixture of both freezing and deposition. But when water vapor in the air comes in contact with cold window glass, loses enough kinetic energy to change directly from a gas to a solid. In our review questions, during the phase change, a substance undergoes a and reversible change from one state to another. Just our definition for a phase change. Why does ice change to water as energy is added at the melting point? And molecules vibrate quicker, motions overcome the forces of attraction. What is the phase change in which a solid is converted directly to a gas? And that's called our sublimation. Sometimes we will see sublimation used both for solid directly to gas, gas directly to a solid. Exothermic phase changes mean energy is being released, and they are released in freezing, condensation, and deposition. D, we shouldn't even consider because it's got fusion in it and not a phase change. The others are not all exothermic. The true and false says a liquid undergoes a phase change to the gas state, its temperature increases, and we had seen earlier false, the temperature does not change during a phase change. So that's our 3-3 notes, and that's all for now.